So last example, I promise, it's the last example. And so what we're doing is we've got we've got an overhanging beam. And so we've got a roller at this end, a pin connection at this end. It's got a point load, it's got a moment, it's got a line load, so it's got a little bit of everything so that we can just go through everything just in a single example. And so what I'll do first is I'll draw the free body diagram to get the reactions. Then we'll figure out what those reactions are. Then we'll do a free body diagram to get the shear force diagram. And then we'll use the shear force diagram to get the bending moment diagram. Okay, so just give me a minute. I'll draw out my free body diagram and calculate the reactions. So I've drawn my free body diagram to get the reactions. So in that one, I can turn this line load into an equivalent point load because I'm finding external forces, so that's not a problem. So we've done that, and then I've worked through and calculated RA and RB. Again, just be careful. This is a pure moment. Don't multiply it by a lever arm. It's only the forces you multiply by a lever arm. Work through that, and then so I've just used moment about A, then I used moment about B, and then I checked it by making sure all these add up to 0. The Y components all add up to 0. And so should have the right answers. So then the next step is to draw a free body diagram for calculating the shear force or internal forces. And so all that happens is I'll put in the values for these. Oh, just one thing. I wasn't sure whether this would be positive or negative, to be honest. This RA, I drew it positive and it came out positive, so I know I had it in the right direction. But it might have been the case if this had come out negative, I'd had to draw it in the other direction and then work through the calcs again. And just noticing, should have some units on those. Okay, so now I'll draw the free body diagram for getting the internal forces, and we'll come back and we'll do the SFD and BMD. So drawing those axes, so let's have a crack at drawing the shear force diagram. So it's, what I've forgotten to do is to draw the free body diagram. 2 seconds. Okay, redrawn it. So the only thing you need to do is to put that UDL back on when you're finding internal forces, or you can just use this one. The other thing that's worth doing is just put on these actual values. So that one there is 6.2 kilonewtons RA, and RB is 7.8 kilonewtons. Okay, so draw the shear force diagram. I need to move this a little bit. I'm just looking at what I need to draw. So where I need to put my axes. So it's going to go up, so that will just do 510. So 510 kilonewtons. This is my shear force diagram. Get out a little bit. And so follow the forces, go up 6.2, so up 6.2. And then keep going until you get to another force horizontally. If there's nothing there, go down 10. So that'll take us down to 3.8. 3.8, somewhere there. So it's going to be 6.2 kilonewtons. 3.8. Keep going until you get to something else. Now we do get to a moment, but that doesn't affect shear force because it's got no net force. So we'll keep going along until we get to 7.8. So this here was 3.2 kilonewtons. Oh no, sorry, 3.8 kilonewtons. Then we're going to go up to 7.8, which is going to take us to 4. So we're going to come up to here. And then we're going to come down by 2 kilonewtons per meter. So that's just going to bring us back to the 0. So we know that's okay, and that would be 4 kilonewtons. Shear force diagram is done. And now we think about the moment diagram. The main thing for this one is this little point load. I haven't done many of those when they're in the middle of the beam. You don't really get them much in real situations. These kind of point moments, I should have said, a couple like that. Make them a bit more mechanical engineering though. Okay, for the bending moment diagram, so it's a pin connection at the end, so it must start at 0. So it's going to start down here. Let me just move this so it's lined up. Then it's going to go down by, so you're just doing pretty much the same as you did to get from UDL to shear force. You get from shear force to bending moment. So it's going to go down by 6.2 kilonewtons every meter. It's going down as positive, so it's going in the positive direction is the better way to say that. And so it is going to end up at 12.4 kilonewton meters, because it's 2 meters long, that little section. 12.4 kilonewton meters, or you could say it's going 6.2 every meter. Then we've got a negative moment, so it's going to come back down again. And it's going to go down by 3.8 kilonewtons for every meter, so it's just the area under here. So 3.8 kilonewton meters for every meter. So 12.4, let's just go all the way to the end. It's horizontal, so it's going to be a straight line. So we're going to do 12.4, and we're going to take away 3.8 times 3. We're going to end up with 1. And so let's just put some units on here. That's 5, 10, minus 5, minus 10. We're going to come back up to 1 here. Interesting. I think it should be 1. Let me just double check that. And 3, that's okay. That's okay, because so I'm wondering why it's not going to work out right, because we've got this point load, and so we need to be careful of that. So we'll go along until we get to that point load, which is at 4 meters, and we're going to go so that's here. So we're going to go down 3.8 for every meter until we get to that point load. And so that's going to be 7.6, 12.4 take away 7.6. It's going to be 4.8. So by that time it's going to get to 4.8, which is pretty much 5 really. Just zoom back in a little bit more. And again, it shows you how important it is to know these little rules. So I was expecting to get back to 0. If I had gone to this point 1, I couldn't see how it was going to get back to 0, because it's going to be going down 2 kilonewtons for every meter. So it's going to end up negative at the end, and it can't be negative at the end because it's got a free end. There's no moment there. And so I went back and looked at it again, and yeah, we've got this 5 kilonewton per meter. So that's going anti-clockwise, so that would be positive. But the bending moment diagram does the opposite, so it's going to take us in the negative direction by 5 kilonewton meters, and it jumps. So it's going to go 5 kilonewton meters, and it's going to jump. So that's going to take us from 4.8. Add 5 to that, or take 5 from that, sorry, you're going to get minus 0.2. And then we've still got this area here, so we have to go up another, what are we doing? 3. Yeah, so we've got this area here, so we have to go up another 3.8, which is in the negative direction. This is a negative shear, and so that's going to take us to 4. This here is going to be 2, I think, isn't it? 4, we're going down to 0 after 2, so that must be 2 kilonewtons. And so the first area is 3 times 1, so it's just 3. So after 1 meter, you're going to have to come down to 3. Just have a think about that for a minute. Go up another 3.8, it's going to take you to 4. Go 3, oh, you're going to come down 3, sorry. So this is going to take us down 3, so we're going to get to 1. Get to 1 here, and then you got this one here, is going to take you down another 1, so it's 2, 0, so the average is 1, so the area is 1. It's going to look like that, and then you're going to draw your line through that as a curve, because that's inclined shear force, not rectangular, it's triangular, so it's going to be a curve. And that's just got the bending moment diagram. I just need to write what that is, and that's 4 kilonewton meters. Then we shade that, and we're done. And we could check a couple of sections, bit of a complicated one, so you might want to do method of sections and check a couple of sections for that to make sure you've got the right answer. And similarly, when you get stuck, you can do, if there's something that doesn't look right, just take a section at that point, figure out what it should be, and then try and figure out where you've gone wrong. Okay, done. Whew.